Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Tim Spiller, Director of the Quantum Communications Hub in the UK. Tim describes the Hub's work on quantum key distribution, QKD, and quantum networking. He highlights the advancements in short and long-range quantum communications, including a CubeSat-based QKD system. Tim elaborates on the transition from research to commercialization within the UK National Quantum Technologies Programme, touching on intellectual property transfer, industry partnerships, and ethical considerations in secure communications. He also shares insights on global quantum initiatives in China, Europe, and the US, future quantum networking goals in the UK, and much more. We hope you enjoyed this episode. Hello, Tim, and thank you so much for joining me today.
Oh, it's very nice to be here. I look forward to our discussion.
So who are you and what do you do?
Okay, well, I'm Tim Spiller. I am Professor of Quantum Information Technologies at York, but I think more for the purposes of this discussion, it's also relevant that I am the Director of the Quantum Communications Hub. Now, that is one of the current parts of the National Quantum Technologies Programme in the UK, which is leading, I guess, the low technology readiness aspects of quantum technology development. So there are 4 hubs in the UK. I lead the one on communications, and each of those hubs is a collaboration of roughly 10 universities plus industry partners plus national laboratories and institutions. And so they're big spread out things across the UK, and we collaborate together to push forward various quantum technologies. So in my case, it's quantum communications.
And when you say low technology readiness, sometimes communications come up as being closer to prime time than, say, computing. What do you mean by that?
Well, what I really mean is that it's understood that the quantum science research that underpins all quantum technologies is done in university labs, clearly elsewhere in the world, but for the UK program within the UK. And we build on top of that to take that quantum science and push it towards having demonstrators of new technologies in quantum communications. We don't turn it all the way into a product. If we are successful in our development stages, then what usually happens is that our work will transfer into another project which might be funded in a different part of the UK national programme, and it may well be led by industry, and that might develop it further. And then if it all goes well, then either an existing company or perhaps a startup that comes out of the work will then take it even further and raise, venture or whatever funding to fully commercialize it. So we do the lower few stages of that and then pass on the work right through the national program so it can be commercialized in the future.
And I believe that you guys are now in phase 2 of the hub, right? Phase 1 was maybe until 2019 or something like that. Is that correct? And what are the goals of phase 2?
Yeah, so the way, the national program started in 2014. The funding was found in 2013. The program started in 2014, had phase 1 for 5 years, has phase 2 for 5 years, and there will be a phase 3 starting shortly, although our particular hub has a little overlap into that, which I could talk about later. But basically in phase 1, we pushed forward various new technologies in quantum key distribution, which was already established as something that could work and be deployed around. And then in particular in phase 2, we have focused on what we've called quantum communications at all length scales. So we've looked at short-range free space handheld quantum key distribution devices. We've looked at further developing what's been done in optical fiber networking, so QKD in optical fibers around parts of the UK. And we've also looked at the longest distances by building both a quantum transmitter and a quantum receiver. The transmitter will go on a small CubeSat that is planned to be launched next year, and we have a quantum receiver that will go on a ground station that can receive those signals. So we want to demonstrate quantum key distribution from a satellite to ground.
A lot of the QKD publications, at least commercial publications, have been around use cases of, say, a large bank needs to securely make transactions, and thus QKD is important. I'm curious about the short range applications that you mentioned. Why would QKD be useful in short range communications?
Well, this would be for consumers or individuals, and so the idea might be that if you want to do future transactions with your bank, or indeed with your employer, or possibly the health service or the government, then if your handheld device is used to share key with any of those institutions, you then carry around, one half of the symmetric key, and those institutions has the other half. You can then use that key to subsequently secure either a financial transaction or some communication about your health and so on, or some communication with your employer, or possibly even to get through the door at your employer or whatever. So shared symmetric keys can be used for quite a number of things, and encryption and decryption is one, but it could get you through the door or something like that. So the idea is that it would be a handheld device that is yours, and you can exchange key in a kind of top-up way when you go to your bank or your employer or something, and then you carry around that your copy of the symmetric key in that device, and you can secure transactions or whatever in the future that could be done at some other place that's connected to that institution. So it's really for individuals and consumers.
You mentioned that Phase 2 is coming to an end, 2024, although there may be some overlap. What does Phase 3 look like?
Well, Phase 3 was officially announced in August, I think, but the process ran for a year or more there, and it's been announced by the UK National Programme, and in particular, it's the Engineering and Physical Sciences Research Council that funds the hubs, this low TRL aspects of the work. And there will be 5 new hubs that all start on the 1st of December. So there's very much a lot of continuity from Phase 2 into Phase 3, but there are genuinely new hubs that are starting up, and in particular, one of them is focusing on medical and bio applications of quantum technology. So that, if you like, is the new one, and then the other 4 are very much an evolution of work that's been going on in Phase 2 into a new Phase 3. I did mention there was one caveat, and I already said that the planned launch of our satellite is going to be next year, 2025. So because we still have some funding left with COVID and everything, people generally developed a bit of underspend in their hubs. What we're going to do is our Phase 2 hub has been given a 1-year extension just on the space mission part, so that we can actually deliver all the way through to the launch of our satellite. And then after that, once the satellite is up there and operational, clearly the Phase 3 activities that are relevant for quantum communications can then, if you like, take over and deliver further work on that. But we've got a 1-year extension of just that part of our hub, so we can deliver our space mission successfully.
How does it work on an IP level? I mean, you mentioned that there's sort of fundamental research in technologies, and then the hope is that these technologies get transferred into the market through startups or maybe program participants that decide to start companies. Do they now have to license the IP from the developing university or from the hub? How does one start a company this way?
Well, it depends how it works. So within within something large like a hub, there are many smaller collaborative projects focused on different aspects of quantum communications. In general, if there is something that focuses on, let's say, a technology development thing where you would expect IP to come out, there will be a sub agreement for that smaller project between the relevant partners. Now, I mentioned that there are industry partners involved in the hubs, so it may well be that there are existing companies that are involved in that particular project, in which case they might already be partial inventors along with university people of the relevant IP, in which case there will already be an IP agreement between the if you like, some of the university inventors and the company that could be doing the commercialization. If it's purely a university thing and or universities and a company doesn't yet exist, then there are mechanisms for creating a new startup at a university. And in general, there will be some agreement between the university or relevant universities about transferring or licensing the IP into the company so it can be commercialized that way. It's also possible that I mentioned we do some level of R&D up to a certain point, and then it could get passed to another project. That project may well be funded by Innovate UK rather than EPSRC, and that would operate at higher TRL, and that would be industry-led, certainly have university partners in it as well. That would have a completely separate IP agreement, and it could well be that new IP is developed within that project that carries the work further towards commercialization. So in general, it's done on a case by case and specific project or specific technology basis. I think it would have been extremely hard for the whole UK national program to have some overall IP management right across the board, because I think companies would have been very reluctant to buy into that when you don't know where you're going. I think it's much easier to have agreements that are done case by case, and then you can choose to commercialize that particular technology on the basis of the IP in that area.
I believe I read that there were some commercial demonstrations in the UK. I think BT and HSBC perhaps demonstrated QKD. To the extent you can share, where is the gap between what you guys are working on and what the commercial enterprises are demonstrating?
I would quote that particular example as actually a hub success, because what happened, I mean, there was preliminary work on QKD both in companies and in universities before the UK national program started. But during the first part of the UK national program, and it carried on into phase 2 as well, we built the UK quantum network, which involved a small metropolitan network around Bristol, a small metropolitan network around Cambridge, and we borrowed bits of the National Dark Fibre Facility, which is an R&D fibre network that EPSRC basically funds for all sorts of networking R&D. We borrowed bits of that to actually connect across between the Bristol network and the Cambridge network, and we also set up, funded on a separate project by EPSRC, we set up a link from the Cambridge network down to BT's Adastral Park R&D centre, which is near Ipswich. So all that was established, and we kind of, if you like, showed the principle, and we clearly had industry partners involved. Those industry partners then took on further work in Innovate UK funded projects to develop that further, and they did some other demonstrations, and then that's progressed now to BT and Toshiba as, if you like, the technology and service provider side of it, running a small QKD commercial demonstration network in London. And HSBC and EY have certainly been mentioned in public as customers. So if you like, we've seen the evolution of the QKD work there go pretty much up the TRL stack, from the research at the bottom all the way to pretty much now commercial technology, which is great. So that's a success story. What's been going on in the hub since then is that we've been looking at further refinements or improvements, if you want, to QKD. So we've done some work on the dynamical reconfiguration of quantum networking, which is, the terminology software defined network. So you can rejig the network in software. We've done some work actually also in collaboration with industry partners on that. We've also started pursuing the distribution of entanglement. So at the minute, all the commercial QKD that's demonstrated is kind of prepare and measure at the other end type of QKD, where you send single photons or single photon-like pulses or possibly coherent pulses. But at the minute, the commercial stuff isn't really functioning on entanglement. So that will be both the focus of phase 3 in terms of the UK national programme, but it has already been the focus of some of the hub work, if you like. So that we would expect to move up in TRL over the coming years. But it's nice to see that some of the basic QKD work has progressed all the way through to commercial demonstration now.
How do you see the focus of the UK program similar or different to other, let's start with Western countries, other countries in Europe or the US? What is the difference between your focus and what you see in other countries?
I'm not sure there's a huge difference in focus. I think we've put a lot of effort into getting QKD through so that, now it's at the demo level with BT and Toshiba and other industry partners. Our focus will now be shifting significantly onto entanglement-based quantum networking. In Europe, I think it's fair to say that has been approached in a similar way. So, within the EU, which we are now not a partner in, within the EU, they are developing the Euro QCI, the European Quantum Communications Infrastructure, which at the minute is very much focused on setting up trusted node QKD links all across Europe. So, that I think parallels very much what we've done in the UK as well. Also, clearly in Europe, they're doing entanglement-based connections between qubits in different laboratories and things. So I think we've done a little bit of that without perhaps the emphasis on the interaction between matter qubits. It's rather been in the UK to distribute entanglement and use it immediately. But I think you'll see in phase 3 in the UK, we'll be focusing more on getting distributed entanglement to interact with matter qubits. So I think there's a parallel there as well. I guess, although QKD, I would say, has not been widely adopted at government level, either in the US or the UK, there has certainly been some QKD trusted node demonstration networks at various points in the US, and the US is certainly now also putting significant emphasis on quantum networking involving entanglement distribution and matter qubits. So I think there are parallels between what will go on in the US for the next few years and the UK and the EU.
How about China?
Well, I would say they're doing the same. I think the one thing is there's been very significant government investment there. So the Chinese put up a substantial satellite with quantum sources on it quite a few years ago, 2016 or so, I think it was launched. So they've done some demonstrations to show feasibility of quantum communications from space already, which is good. They've built a very substantial trusted node QKD network from Beijing to Shanghai. So I think what's being done is similar. They've done it at a larger scale with I think greater investment. And that's probably at the minute because there is more backing, if you like, from the Chinese government to actually push QKD alongside other forms of future secure communications that will be proof against quantum computer attack.
We were talking about communications, long range, short range, but one area that seems to intersect with quantum computing is actually connecting quantum computers with some kind of network, whether to scale up their capabilities in the case of superconducting or trapped ions or others. Does your hub also deal with that application of networking?
Our current hub doesn't. The evolved version of our hub in the next phase of the UK national programme certainly will. So in the 5 new hubs, there will be one that focuses on quantum computing and one that focuses on quantum networking. And they are both very much aware of and addressing this particular there are two. I'll pull apart a technical difference in just a minute, but it's worth also noting that as well as putting in place new hubs, the UK national programme has these framework entities called missions. There are 5 of those as well, and there is a mission on quantum computing and a mission on quantum networking, and those are making sure that the quantum networking, in the sense that you just alluded to, will be covered and will be addressed. Now, I think there are 2 different aspects to it that are worth pulling apart. If you want to connect quantum processors together that might be, in different fridges if they're superconducting processors, you might be able to do that connection between fridges that are essentially in the same laboratory or same room by microwave links from one to the other, or possibly transduction from microwave to some other frequency, and then short-range quantum communication to the other processor. That's all very well, and the focus there is to be able to connect coherently over a short distance. If you want to connect 2 things that are, let's say, 50 kilometers apart, you're almost certainly going to be having to do that down fiber and with telecom wavelength photons, the sort of photons that travel down fiber. Now, that may well mean that you've got to frequency convert. So if you want a quantum computer in one place in the UK to talk to another one, whether that's to get a bigger quantum computer or whether it's to allow secure and private access to a quantum computer over distance, you're going to have to use telecom wavelength photons, I think, for the longer distance communication. And probably, given the kinds of things we're using for quantum computing qubits at the minute, almost certainly that will need frequency conversion, because the kind of frequencies that qubits work at are not the kind of frequencies that we propagate down telecom fibers. So there will have to be some clever stuff done with converting the photons in frequency, probably at both ends, if you want to get one computer to talk to another. So pulling those 2 apart, I think it's likely that in the national programme in the next phase, the shorter range networking between 2 adjacent fridges will be handled in one hub, and the longer distance networking, where you have to worry about quantum memories or frequency conversion, will be handled in the other hub. But I think it's fair to say that the UK's got it covered. We're aware of these distinctions, and both aspects of networking will be covered in the next phase.
You've been doing this for a number of years, even in the context of a hub, and much longer as a physics professor. What have you learned about quantum networking in the last, say, 12 months that you didn't know prior to that?
That's quite a tricky question. I think it's going to be quite hard work. I think the more you dig and think about the challenges, the more you see there's still quite a lot to be done. So, naively, if you could just take photons out of a qubit, shove them straight down a fiber and put them into a qubit at the other end, it would be relatively straightforward. It's going to be rather more tricky than that at the moment. So I think there are lots of engineering challenges that the more you look, the harder they seem to be. But then, we've overcome lots of things in the past. So I'm optimistic, but I think it's going to take quite a lot of work. So I think that there's a lot to be done. I mean, I think we've achieved a lot in 10 years. I think there's a lot to be done in the next 10 years.
As we get close to the end of our conversation, I wanted to ask you a question about ethics. In computing, there's a big discussion about ethics because quantum computers could be used both for wonderfully good purposes as well as for wonderfully evil purposes. Does the ethics conversation also permeate quantum networking?
Well, it certainly has from the privacy aspects of quantum communication, because but I don't think this is just a quantum ethics thing. I think this is a general secure communications ethics thing, and I think the UK has to decide whether it wants secure communications to be accessible and interceptable in cases where there is something suspicious potentially going on, or not. I mean, if we offer genuine end-to-end security to individuals, then we can't look at what they are communicating with each other. And so, people kind of want to have their cake and eat it. They say, well, it's all right, I would like my end-to-end security, thank you very much. On the other hand, I don't want criminals to have end-to-end security. I want that to be interceptable in the middle. Well, either we have a system where you can intercept in the middle, or we don't. And so, a trusted node approach with QKD, in fact, kind of gives you that, in that you could, at points where there are trusted nodes, you could ask the service provider to effectively provide access to what went through that node at that point. On the other hand, if we have quantum repeaters in the future, we might be able to offer genuine end-to-end quantum security. And so I think that's, we are aware of that, and we know what technology we are developing. I think in the end, the UK has got to decide what sort of secure communications it wants. Does it want the right to lawful intercept on anyone's communications, or does it want end-to-end security for individuals? And I think, I know it's passing the buck, but I think in the end, the government's got to decide on that. I mean, the technology can be there, I think, to deliver either way forward, and then we have to have a decision about which one it's going to be.
In last hypothetical, if you could have dinner with one of the quantum greats or communication greats, dead or alive, who would that person be?
Well, it's not just quantum communication. If I go all the way back, I think my heroes are Einstein, Dirac, and Feynman. It's hard to pick out three, but those have always kind of been my favorite three in terms of what they contributed in various ways to quantum. So Einstein usually comes out top. So I guess I would pick him. But if it was three, I'd pick those three. Although I understand Dirac probably wouldn't have said very much at dinner, as he was rather quiet and reserved.
Wonderful. Tim, thank you so much for joining me today.
Thank you.